Okay, so I'll focus on this one here. Sorry about the slides. So we just rebranded to black backgrounds, and it's getting a bit lost with the light. This is what we call evidence-based, human-centered, augmented intelligence. So there's three things that we think about currently when we are looking at building design. The first one is how to achieve sustainability. To really achieve sustainability, we have to focus on going beyond it. We have to think about regenerative design principles. And it has to be from an evidence point of view. This building design, in many ways, comes from experience and based on assumptions. And sometimes, most of the time, we have very small fees at the beginning of the project to bring all of our knowledge and design more efficiently. So we end up making assumptions to simplify that process, and then we find the problems later. What we're trying to bring forward to the beginning of the process is that evidence, is data. When you bring data and regenerative design principles together, you end up with what we're calling performance-informed, human-driven. This is just the introduction. I'm just going to be brief about this, and then I'll explain a bit more in detail, so just bear with me. So, performance-informed, human-driven. Now, the next frontier is how do we enhance our intelligence with the use of automated tools and AI? And that is what we call augmented intelligence. So, the new paradigm in design and sustainable design is a combination of all of those aspects, which is what we call, and I'm sorry, English is not my first language, so I have to breathe to read this, performance-informed, human-driven, augmented intelligence. I know it sounds like a long title, loads of buzzwords, but it is how we need to start thinking about buildings. And hopefully from today's presentation, you'll see how, step by step, little by little, we're starting to do that. The current context is really challenging. So we have to focus on time, cost, and quality. Those have been always the drivers for building design, and that's always a challenge, to the extent that sometimes we make a joke. We make a joke that you can only get 2 of those, not the 3 at the same time. So from the beginning, we're setting ourselves to fail. And currently, it's even more complex. We need to also think about the performance of the building, which is embodied carbon, thermal comfort, daylight, operational carbon. And on top of that, place-making principles, such as circularity, toxicity, energy generation, etc. So building design is becoming more and more complex. And all of these aspects are interconnected in ways which is not always intuitive. Sometimes improving one aspect affects negatively the other. So the context for building design is becoming more and more complex, and clients are expecting us to optimize all of this at the beginning when our fees are a bit small. So it's becoming a real challenge. So I'm going to pause this for a second because I want to ask you a question. This is a bit of a test. Not really a test for you, but see how we're thinking. For us, this was the eureka moment. Now, we got 3 sides of the room. So those on that side, you are the architect. Now think about, it's the same brief, 20,000 square meters, forget about the actual number, the same area for the 3 groups. And the architect has the mission to make this office building, to have floors that have the most access to daylight. So if you're thinking about daylight and you're optimizing daylight for your offices, what shape would this building be? It would be possibly slender, skinny, tall, so you can have access to daylight. You think about the architects. Now, you will be the structural engineers. The same challenge, what would the building look like if you had no constraints, no side constraints? Would it be tall? Would it be skinny? Does that use more concrete than a flat level building, than a low-rise building, a campus-style building? Oh, going back, sorry. And then this side of the room, you're the mechanical engineers. So how do you create a building that has the least amount of energy? That is your objective. And then the question is, would those 3 buildings look the same? Would I'm seeing people being like, no, and I think you're right. And what we did was we decided to start optimizing those processes, and we created algorithms to optimize each of those. This is a genetic algorithm testing different massings and different orientations, facade types, performance of the facade, and then each of those factors was being optimized. Daylight, operational carbon, and embodied carbon. And as you can see, when we found the most efficient shape, they were completely different. The architectural one looked like a tower. The engineering one, the structures, looked like a campus style. But that is not very good for energy or for daylight. And the mechanical engineers, any mechanical engineers? Well, if you want to completely isolate your building from any solar gains and energy losses, you create a basement, and it's buried in the ground. But that's not very pretty for an office, right? And it's terrible for embodied carbon because it's a massive basement with basement walls. So the point here is, if you have three main building disciplines and you ask them, give me your best product, give me your best product, give me your best product, they will be pulling in completely different directions. That is the challenge of building design. We have to find the way forward that is the most efficient for all of them simultaneously. And the reason why buildings look the way they do, which is almost like the one on the left, is because one discipline typically comes first. It could be architecture, it could be cost planning, it could be the municipality defining some parameters. And the design process is linear. And what happens is that the engineering comes after, and we have to then fight against building physics to make it work. And sometimes structural engineers have to fight against gravity to make the building work. And that is a real challenge. That is not how it should be. We should, and when you try to optimize one of those variables, then the others change in a different way. And when you do that at a detail stage, it's costly, it's inefficient, and it's frustrating. So what is the solution? We thought, what can we do? So let's create another algorithm that simulates these parameters simultaneously. And then this was a first try back in 2023, a few years ago. And we created a little algorithm that was testing. And every generation of the simulation would create results. Each of those points in the graph is a different test of the massing, shape, orientation. So for each of those options, we evaluated performance in the three objectives. So now what you see is a surface of all the possibilities. Building design traditionally was just about the architect, the mechanical engineer, the structural engineer suggesting 2-3 options and then trying to go from that. What that means is that you have 3 options and you explore those 3 and you can only optimize around those options. What this is doing is creating the entire surface of all the thousands of possible options. And it's done in a matter of minutes because we created an algorithm that could simplify that design process. This is not detailed design, it's just an estimation to give a sense of direction. And what it does is it allows you to evaluate the outliers, something you could have never thought about maybe, because it wasn't intuitive. And I'll show you a few examples of how we've been doing this with clients in a moment. Now that you have all that data, then you can select which of those design options meet the criteria. And this is what we call evidence-based design. It's not just about intuition. And in building design, we use our intuition, we use our experience, and that is fantastic. But that intuition and that experience comes from what we have built before. And sometimes those examples are good, sometimes they're not that good or could have been better. So we bring all of our biases to building design. With these tools, we can explore the complete design spectrum and find better solutions. So this framework of using evidence to create multiple options and multiple simulations is what we're calling co-design. I know there's a few definitions for co-design, but we thought this was the most appropriate one. And it's about, and I also have to breathe to read this, it's a system-level integrative design approach that unites multiple disciplines to collaboratively address the complexities of whole building performance. The key points here are multidisciplinary, so all disciplines thinking about the same objectives. And the second point is whole building performance. It's not about just optimizing one parameter. Buildings are a system that interact a system of different aspects that need to perform in a collaborative way, need to perform together using evidence. And this co-design approach is based on 3 pillars. The first one is it has to be multidisciplinary. I think I've said that word a few times now. The second one is early stage asset simulation, which is something that doesn't happen that often because we don't have the fees at the beginning of a project. We don't have the time to simulate. So bringing that idea of generating computational models that can evaluate those parameters to the beginning of the process is really powerful. And finally, that leads to data, that leads to what we call evidence-based decision-making, so that the design process becomes a coordinated collaboration between all the disciplines and with sustainability around them, bringing them all together. So I'll give you some examples of how we've been doing this with some clients, because it's easy to say, yes, let's do something simultaneously, let's optimize at the same time. It's easy, but how have we actually applied this in a few projects? The first one was, not a fire alarm, right? Okay. The first one was, the client had a challenge. They had an apartment building. This is an apartment, it is just one apartment in a group of 6 apartments per floor. I think it was 20 stories of the building. And they said, we have submitted this for municipal approval, and the municipality says that our windows are too small. The apartments do not get enough daylight. But if I increase the size of the windows, my apartments are overheating. And in the UK, we try not to have air conditioning in apartments, we try to design that out. They said, if I increase the window size, I'm going to have to install air conditioning in these apartments, and it's not feasible. So what can I do? And what they thought they could do to meet all of those criteria was, let's increase the window size, and let's put like a film in front of the glass to reduce the amount of solar gains. And it wasn't looking great. So they said, help us. How can we use this co-design framework you've been talking to us about to address this specific project? So this was the first project we had with a client. And what we did was we created a parametric model of each apartment. So as you can see here on the right-hand side, every aspect of the apartment facade, the window size, the shading, the glass type, the thickness of the window was modeled and then was iterated using a genetic algorithm. So we created nearly 2,000 combinations of possibilities, as you can see on the right-hand side. And with all that data, we could inform the client by filtering those parameters that met the criteria, what to do. And in this case, what we ended up doing was we actually said to the client, make the windows smaller. And I thought, what? This is completely against what we've been advised to do. And in a typical design process, which is a linear process, poor daylight, bigger windows, more energy, air conditioning. That was inevitable. What we said was smaller windows, but change the glass type to achieve a different performance with a different transparency so that you get the same amount of light, but less, and install a different shading device, and you get the same amount of light, but less energy consumption. And the planning authority, I mean the municipality authority, we had to justify with this evidence why we were going against their advice. But this building performs exactly how the client needs it to perform. And we did this through an early stage iteration. So that was the first time that we applied this, and we went to the municipality and we proved to them that it would perform even better in terms of daylight than the option that was being suggested. So that was the first time that we implemented these techniques, and then the client was very happy and said, I have another project. In this case, this is a whole floor of a 30-story tower in London. And because it had fantastic views, they wanted full-height windows. And what happens when you have full-height window glass, a lot of daylight comes in and it overheats, and you need to cool that down mechanically. And I know that we're used to mechanical cooling, but in the UK, it's frowned upon. It's very strange that you have to do that. So the client was really trying to reduce that. So we did the same, and we created a parametric model of the whole floor, where every aspect of the floor, the window size, the window thickness, the glass, the type of glass, the balcony size, the shading devices, They were all parametrically modeled and iterated, and we created hundreds of options. So what we do then is, from those options, we create the entire surface of possibilities. The dot that you can see there at the top was the initial architectural design. And this is no criticism to architects. This is just what their vision was, to achieve something great, and that is performing very well in several aspects. In terms of daylight, it's performing really well. In terms of embodied carbon, it was performing very well. You got embodied carbon on the x-axis, energy in the y-axis, and daylight in the z-axis. But in the color scheme, you see the yellow and the purple. The yellow is the massive, the greatest amount of heat, of overheating. So it wasn't performing well. The apartments were overheating. So what we then do is we start filtering those parameters, and we bring the client and the architect and the rest of the design team, and through this data-driven approach, we start filtering. Filter performance in the x-axis. That means I have selected what range of embodied carbon I'm happy to accept as a project. And those are the options that work. And then you filter again in the y-axis, and you say, I am selecting the energy into the EUY that complies with the brief. And from those, you're selecting options that meet that design brief, and those are translated into interventions. So don't focus too much on the graphics. If you want to, on the south facade, we recommend these interventions. On the east facade, we recommend those interventions, etc. And what the client can do now and the architect can do now is, from this evidence, which is not intuition, it's data, they can make better decisions. And they can choose what aspects of the recommendations they bring in, and then we reanalyze the model, and then we have a project that meets that performance brief, and it was all from data, and all of this happened at the beginning of the project, before any of these big decisions were made. So cost was saved, performance was achieved. That is how we start seeing design happening more and more, bringing the power of automated tools to really help us have data to make those decisions. So then another client said, now I have a master plan, and I'm really struggling to achieve the balance between how much daylight my apartments get, how much heating I need, how much cooling I need. How can you help us optimize? So the first question we asked them was, well, what can I play with? At what stage are you? And they said, we are already at a schematic design stage, so we can't really change too much, but you can play with the heights of the buildings. So we created a different parametric model where you can see on the right, each of the buildings, we played with the height of them, and every time you change the height of some of those buildings, trying to achieve the same area, we assessed the same performance parameters. And we created hundreds of different possibilities in a few hours to show them what they could achieve. And the results from this was very, very, very similar to the original. We just made a few tweaks. One of the buildings was shorter, one of the buildings was higher, trying to optimize that interaction between the building height, the shade that provides, and the heating and the cooling. But what this represented, because those were the optimization parameters, is we saved carbon emissions, 180 tons of carbon emissions. It also meant that the energy use, the energy need for this building for heating was less, so that reduces heating bills, whilst reducing the overheating so that we didn't need air conditioning. But the unexpected win was that something that we hadn't assessed, it was just a happy mistake, was that because we had all that data, we thought, what if we could also measure the area of facade in each of those options? And we realized that for this one, the area of glass was less, which meant the client was able to save £500,000 because there was less facade elements. And we only charged them, I think, £20,000. And then they said, so that's again another argument for the importance of early stage design. Our fees are so tiny compared to the improvements that we can bring. And so the client was so happy about it. I said, what else can we do? And then they appointed us to look at one of those buildings, but at every apartment. They said, I want this analysis, all this combination of analysis for every apartment. Because of that shape of building, I have apartments who are south-facing, southwest-facing, north-facing, low, mid-rise. They all perform differently. So the first thing that we did was we clustered the apartments to understand similarities in performance. So different colors are apartments who perform similarly. And that way we can simplify the computational process. And from there, we analyzed, using the same methodology, parametrically, each one, evaluated their performance, and we could then give advice of what interventions to make to each apartment, to the type of glass, the type of shading, the type of window, so that we could improve that. So for example, for some of the buildings that were on the north side, in the UK, north-facing buildings, they do not get as much sun most of the year, and we needed to improve that daylight, so we had to change the glazing ratio, the size of the windows. If you look at southwest-facing or west-facing apartments, we could improve the daylight, but also we had to balance against the overheating potential. But for us, it feels intuitive, it feels obvious. The one thing that we learned from this project was that for some of these apartments, the ones facing north, the ones that do not get as much sun in the winter, what was happening with them was the opposite. Because they don't get as much sun, their heating demand was so high because they never got that extra amount. And if we increased the window size to get more daylight in, they were losing heat as well, so that we needed to heat them up with more equipment. And that was because the apartments had a specific layout. Typically, apartments, like one-bedroom apartments in the UK, they are living room, bedroom, bathroom, kitchen. There are one single-aspect apartments. They're possibly 8 meters wide and possibly 9 to 10 meters deep. So the back of the apartment was never getting enough daylight. And because of that, there was this vicious cycle of not converging to an answer. So what we said to the architect was, let's change the shape of these apartments, make them narrower so that you can get more daylight without the consequences of bigger windows. And that was something that I don't know why we didn't think about before. It was so obvious now that you see it, but it takes data, it takes evidence to show what that is. The final case study is what we did for the National Health Service, the NHS in the UK. They came to us and they said, we're building many hospitals across the country. We have almost finished designs. As you all know, hospital design is a complicated science that depends on which rooms and which wings are next to each other, what they call adjacencies. And that combination is a real challenge. We have 9 designs, they said. What can we do? Because we're struggling. When we look at those 9 designs, there are like 9 options. So when you plot their performance into a graph, you can see those discrete points of performance. In this case, in terms of embodied carbon, daylight, and overheating potential. So they were struggling because the option 6, which was the one that performed the best performance in terms of daylight, bigger windows, great patient experience, is also the one that performs the worst in terms of overheating. So they needed much more energy to cool these buildings. And if you think about 3-4% energy demand increase across several hospitals across the country, it's a lot. It's a lot of energy, and it's a lot of money that our health service doesn't really have. So they couldn't make a decision. What can we do with these options if the one that we like the best, performs the best in terms of daylight, is the one that performs the worst in the other aspect? How can we achieve that? So we said, right, give us your models, and we're going to create many iterations with those. So all we did was started rotating them, modifying them slightly, and evaluating that performance. The importance here is that we started with 9 options, and now we have 900 options. And as you saw from the previous graph, those 9 options were discrete points in this graph. The 900 options complete the whole surface of possibilities, which means now you can choose from in between those options. And as an engineer, this is absolutely wonderful because now we can see what improvement looks like. So if you look at the graph on the left, option, I can't think it's 3, I think, Option 3 started here, an improvement to option 3A, bringing the graph closer to the center. That is good performance. It meant that all we had to do was some small tweaks to the massing. You can see those massings at the bottom left, very, very similar, but you're improving performance massively. It's so obvious in the graph what improvement means. For the second option, the one in the center, all we had to do to bring that dot 6 to the center of the plot is the same massing, very similar. It was just rotated by 20 degrees. That is, for me as a structural engineer, it's like amazing to see that now I have all the data, like a bit of a nerd, all the data, all the dots to bring them together, and that shows performance. So what we said to them in the end was, all you have to do is rotate this building by 20 degrees, and suddenly you are improving and you're reducing your energy bills by 7% across the whole complex. And 7% across the whole NHS is an amazing amount of saving, much more than anything we could do. So that is the power of the work that we do. And I say we, and I mean all of us in this room. As designers, that influence is the influence that we have, the power to change and reduce carbon emissions at a great scale. And if we can use data to make better decisions, well, that is the future. So then we thought, let's play with this a little bit more. What can we do? Let's try to design our own hospital, creating an algorithm to move the rooms around to make the most efficient hospital. And it starts doing something like that. And every time you move those rooms, it creates different floor plans. And it became quite complex, and we realized, well, we haven't got paid to do this, so we'll do that later. But it gave us a glimpse of what the future of building design could be. It could be an iterative process that is supported by automated tools, by AI, to help us make better decisions. And that leads to a change in the design paradigm. Because currently, building design begins as the dream, the architect's dream, the client's dream, etc. And then we spend the whole of the design process value engineering, which is an awful term because we're not really engineering and not really adding any value. We're changing the specification to reduce cost. And we spend the whole process reducing cost until we get what we can pay for. And that makes the design process a journey of disappointment, a journey of sadness. It's so frustrating to design. What we can do using automation tools and AI is to begin and start with the most efficient. And many architects in the room might think, well, the most efficient is not necessarily the nicest, and I agree. And it's not necessarily the one that meets the client brief. But from that starting point, the most efficient solution, you can then make decisions from data, with data from evidence, to improve performance, to increase cost, to increase duration, to increase carbon emissions if needed, until you achieve the best possible product. So buildings, they are products. And this way, the design process becomes a journey of growth, a journey of joy. And how amazing would it be if every building we designed, we started with something that was maybe a bit ugly, but very efficient, and then you just make it better and better and better. So that would be so much fun to watch and to build. So that is the whole idea that we're trying to change in the current context. And this is happening with the support of automated tools and AI. So the last few slides are about that transformation. How are we going into the future and into a world where AI is growing so quickly around us? And the first thing I want to answer is that, no, we're not replacing us with ChatGPT. That's not happening. And for many reasons. First, because it's not supposed to do that. And some of my engineering colleagues, they find so much joy in breaking ChatGPT, right? And they say, oh, I asked it to design this and it didn't do it. It's so bad. You think, well done. It's like asking a 6-year-old kid who's just going to school, oh, solve these equations. Of course they're not going to know. Eventually they will. But we're not replacing the design process with a large language model because they're not supposed to do that. But we have to embrace that these tools are happening and they're here and they will support this journey, what we call the augmented intelligence. It has to augment our intelligence. The process that we're following is we're trying to make the process better. So this is very roughly what the design process looks like. for an engineering project, and you have all these different activities from the hand calculations to the modeling and the detailed design and creating reports, all from your brain to site is all this process. And we already use automated tools. We use software. We use tools to do each of these steps. But the challenge that we have is that they are connected by hand. So how many times have you exported something from one piece of software to another using Excel and then creating a document and then moving it somewhere else? How many times, hopefully not many, have you missed one column or one row? I mean, I remember I've done that a few times, and you realize, this is just not working because there's so many sources of error. So how we see the transformation into an AI world now is a two-step process. The first step is to create solid tools that can become like building blocks for each of these processes. So you automate, you create a modular automation tool that does specific elements of the design process. So you're not asking ChatGPT design this building. That's not the point. You are creating an automated tool that does an aspect of the design. And then what we are trying to bring is AI agents that connect them. So that way you know that when you move data from one point of one part of the process to the next one, there is fidelity. You know exactly that it's going to the right place. We're connecting them using AI agents. Now that is the beginning. Those are the building blocks to what we call the digital colleague. So when you have automated processes connected with an AI agent that you have created, you can rely on a process that is validated and is doing what you're expecting to do. And that digital colleague then becomes, doesn't replace one of us, it enhances what we can do and we can achieve from that perspective. Then we become the managers of those agents and the managers of those colleagues, and we become the professionals who run these digital design teams. Because the idea of the augmented intelligence process, the idea of bringing automation and AI is that we, the engineer, the architect, the designer, stays at the center of that process and takes advantage of these tools, of the data, so that we can achieve that final objective, which is better buildings. It's changing so quickly around us, but it's not scary. Many, you hear the term AI anxiety a lot recently. I think it's the opposite. I think it should be embraced. I think we need to see this as an opportunity to really drive efficiency, drive value, and create better buildings. When I share this with the next generation, with university students, I tell them there's never been a more exciting time to be a designer, to be an engineer, because we are right at the center of change. If you think about a tall building, like many of the tall buildings that you are currently, designing and building in Tel Aviv, if you save 1% of carbon emissions in one of those buildings, that is equivalent of 100 years of your life as an individual in terms of carbon emission and your carbon footprint. So your carbon handprint and what you can do with that is hundreds of times more important and more impactful than your actual personal footprint. And that is why this time, with these tools, with this context, is such an exciting time to be an engineer, to be an architect, to be a designer, because we can really make a difference. And the fact that you're all here in this room is because you want to make that difference, and you are making a difference. So thank you so much for allowing me to share this with you, and hopefully this leads to much better buildings in your future, in our future. Thank you.